On April 1st, 2026, NASA launched Artemis 2.
1. Booster ignition. And liftoff. The crew of Artemis 2 now bound for the moon. Humanity's next great voyage begins.
This is a simulated flight path for the mission. In mission design, curves like this are called reference trajectories. They represent the sequence of maneuvers the spacecraft is supposed to follow. But looking at a trajectory this complicated raises an immediate question. Out of all possible paths, how do you decide what this one should be in the first place? If your only goal is to leave Earth, loop the moon, and come back, there are many ways to do it. But a real spaceflight is pinned down by strict physical boundaries. And on top of just surviving, you want the trajectory to be as efficient as possible. The goal is not just finding a path that works, it is finding a path that balances all of these limits. This elevates the task from basic orbital mechanics into the mathematical realm of a trajectory optimization problem. If you dig into a NASA paper on the Artemis trajectory, you will see the authors explain that the mission was designed using a multiple shooting approach. That might sound intimidating, but let's take a minute to unpack the mechanism inside this idea using a much simpler one-dimensional problem. Imagine a car moving along a perfectly straight road. We model the car's state with its position and its velocity. Its control is acceleration, basically how hard you're pressing the gas or the brake. Now suppose I want the car to start from a standstill at position 0, and I want to park it exactly 100 meters away, also at rest. And I want to do it in the minimum possible amount of time. In this case, our acceleration is bounded between -2 and +2 meters per second square. The dynamics of the car are quite friendly. This simply means if you know the current state and the control, the future motion is strictly determined. In this example, multiple shooting chops the timeline map into pieces. Let's split our time horizon into 8 little intervals, and we choose this initial guess deliberately. In this example, our guess is very simple. We set both position and velocity as steady upward ramps. For the control, we slope the guess from a positive acceleration down to a negative one. And we will just throw out the guess that the final time is 18 seconds. At iteration 0, I just want you to picture how these guessed variables are sprinkled across our time horizon. You can also see it tracing a predicted path forward, leaving us with a series of disconnected, jagged gaps. To see exactly what is happening under the hood here, let's pull out just one of these intervals and dissect it. Take the state at the left node. We have our physical rules, the dynamics. Using standard numerical stepping rules, for example, Runge-Kutta 4, gives us a predicted landing spot for the next state. For this whole sequence to represent a real physically consistent path, that predicted endpoint has to land exactly where the next node we guessed. If they do not match, the difference between them is called the defect, the gap between where the math predicts the state should end and where our next node currently is. That is the key idea behind multiple shooting method. If we drop back into our main timeline and zoom in, you can clearly see the mismatch in position. The propagated endpoint completely misses the next position node. And here is the exact same physical mismatch in velocity. Now we step into iteration 1. This is where the solver looks at all of those disconnected gaps and calculates exactly how to nudge our guesses to make them fit. The heavy lifting here is done by a nonlinear programming solver, typically using algorithms like the interior point method or sequential quadratic programming. There are some fantastic videos on YouTube if you want to look deeper into how they work. The main takeaway is that one iteration is simply one complete update across our timeline. As the iteration roll by, watch the defects shrink. Eventually, all those separate interval pieces stitch themselves seamlessly into one continuous trajectory. Look down here at the control sequence. To get the car exactly 100 meters away in the shortest possible time, it presses the gas pedal down as hard as the engine allows until exactly halfway through. Then, it switches to the other extreme, braking just as hard until it slides perfectly into a stop at the finish line. And our solver discovered that entirely on its own. But now, what happens if we step up to something much harder? This is a simulation of a rocket coming in for a landing. It has to fire its engine to slow down, swing its nozzle to steer, and hover perfectly upright, exactly on the center of the landing pad. We use the same general multiple shooting framework we just built for the car. In this simplified landing model, Our state now has 6 dimensions: lateral and vertical position, their respective velocities, the tilt angle of the rocket, and its rotational spin. And our control has 2 dimensions, the thrust of the engine and the gimbal angle of the nozzle. The dynamics of this rocket are heavily coupled nonlinear equations. So our exact physical problem is this: find the thrust and steering sequence that land the rocket while minimizing a combination of the total time and thrust. But computers cannot directly optimize truly continuous curves. We have to translate this continuous real-world physics problem into a finite grid of numbers that a computer can actually process. This discrete problem is what we actually hand to our multiple shooting algorithm. We divide the timeline into 30 intervals. At iteration 0, our initial guess is wonderfully naive. So let's just kick off the optimization and watch it work. When the solver finally converges, it forms this seamless trajectory. A real lunar mission operates on a vastly larger scale, broken down into multiple complex flight phases. But the underlying mathematical engine is fundamentally the same as what we just built. Thanks for watching, and I'll see you in the next one.